The first speaker is Professor Ioannis Samarinos. So he obtained his PhD in 2001 from Pittsburgh University after he worked as assistant professor at Vanderbilt University. He joined University of Crete and now is a professor of Department of Computer Science. And Ioannis developed one of the most famous causal discovery algorithms, the max-min hill climbing algorithm. And he is also a founder and CEO of Gnosis Data Analysis and is very active on applications of machine learning and causal inference in biomedicine, as well as machine learning and causal inference methodologies. So today, Ioannis is talking about TOE's automated causal discovery and learning causal dynamical systems. So thank you, Yanni. You have the floor.
Thank you. I hope you can hear me. You can see my screen. And let me start by showing you a short video. And in this video, this is our tool for automating predictive modeling. It's what is called an AutoML tool. There are other tools like that, but I want to show you where we are in terms of automatically producing predictive models. So here in this short video, I'm showing you how you can create a predictive model from Alzheimer's data, where they do some about 500 measurements of molecules in the blood of people with and without Alzheimer's, and they want to figure out which of these molecules actually predict diagnose who has Alzheimer's. So this is what the tool looks like, and you could go to add the data, you upload the file. This is an Excel file, a CSV, you drag and drop, and then you get to see your data. This is a 5x5 portion of the data. We only see the first columns, but there are 500 columns. And the first one has the disease status, whether you have Alzheimer's or not. So you just select whether that this is the variable that you want to create a predictive model for, and then the system runs. And as we can see here, I paused it. It tries to fit lots of different types of predictive models, cross-validate them random forest, support vector machines and the like, and choose the best one for you and for this type of data specifically. Okay, and in the end, we get a predictive model after a few minutes. And here I'm going to use the predictive model. These are the molecules selected out of the 500. We enter the values for a new patient, let's say, or a healthy control, and then we apply the model and we get the prediction. Okay. And then the tool also reports a bunch of other useful information, like area under the curve and ROC curves and the features that were selected and all sorts of metrics and the like. So my point is that automated machine learning for predictive modeling is here. And there are many other tools AutoScikit-learn, of course, is the most widely used library in academia. And the question is, can we do the same for causality? And this is what I'm going to be talking about today. Can we automate causal discovery to this extent? So I'm going to be presenting a joint work with my student Kostadina Biza and my former student Sofia Triandafilou. It's been published in this conference, and now it's been submitted to a journal. Sorry, it has a mind of its own. Okay. It's maybe I'll use this one. I don't know what's happening. Why it's keep moving the slides? Okay, I'll just use like this view. I'm sorry. I hope it's still okay. So the thing is, like, we have a lot of causal discovery algorithms, and they're published like every year, many of them, and no one is better than everybody else, like on all problems. They make different assumptions, and for different problems, like the assumptions are more suitable and they give better results, and in other cases they don't. So when we have a data set, like in this case, we would like perhaps to apply lots of different algorithms like you see here, and each one of them has a bunch of hyperparameters that we need to tune and set the values of, like the independence test that we use in the significance level. And I will be using the terminology configuration to imply a given algorithm with its hyperparameter values, meaning a pipeline that takes you from the data to your causal model. So we can have a lot of different configurations, and they lead to different graphs. So the question, of course, is which one is the best configuration that leads to the best causal graph for a given data set. And the problem, the tuning problem, I call it the tuning problem, is to find this optimal configuration. Now, of course, the issue here is that the true graph is unknown. So we are talking about like an inherently unsupervised learning problem. The standard tricks of cross-validation and things like that don't directly, at least, apply to this problem, just like in clustering, let's say, or dimensionality reduction. So how can we solve this problem, and how can we tune our choices, our algorithmic choices for causal discovery, and make a step towards automating like causal discovery for the non-expert? So the main intuition here is that causal graphs make claims for the Markov blankets. So let's examine this statement like in detail, and start with what is a Markov blanket. Well, the standard definition is that the Markov blanket of a variable vi is a minimal subset of variables that renders all other variables conditionally independent from vi, meaning no other variable gives you more information, additional information, once you know the Markov blanket. This is a probabilistic perspective. We can have an equivalent definition for Markov blanket from a predictive modeling perspective. So if the other variables don't give you extra information, that means like the Markov blanket variables maximize the predictive performance for VI under some conditions, some mild conditions. For example, the fact that you can you use an optimal, let's say, classifier. Okay, so a causal model induces a Markov blanket for each variable. For example, and we can read this from the graphs. Usually there's enough theory to read the Markov blankets from the graph. So in a Bayesian network or a maximal ancestral graph, which is Bayesian networks with latent variables, if you like, the Markov blankets are read from the graph as the nodes that are adjacent to the node. So for node 4, the Markov blanket is the node adjacent to it, like 1, 2, and 7. And the nodes reachable to the node through a collider path. So 5 reaches 4 through a path that only goes through colliders, and so it belongs to the Markov blanket. So now the causal graph claims, this causal graph claims that all we need to optimally predict 4 is the Markov blanket variables 1, 2, 5, and 7. And adding any other variable to this set is not going to increase our predictive performance. So the main idea is to, for selecting and tuning, is to test whether the configuration, the algorithm that we use, gives a graph that stands these claims. So let's see. The first step is that each configuration leads to a causal graph, and each graph induces a set of Markov blankets, one for each node. So we can actually fit a predictive model F for each node, given its Markov blanket, and estimate its predictive performance. I will call predictive performance of the whole causal graph as the average predictive performance of these models over all nodes. So if the estimated Markov blankets are actually correct, then the predictive performance of the graph will be the maximum. And we can use that like to choose the configuration that leads to the graph as our optimization principle. Choose the configuration that leads to the graph with a maximum predictive performance. Now, unfortunately, the reverse doesn't hold, meaning like other graphs can also achieve like maximum predictive performance. So we're going to see how to solve this problem. Okay, so like the algorithm that I'm going to be presenting, it's called out-of-sample causal tuning. And this is like the first building block. The first problem to solve is how to estimate the predictive performance of a configuration on unseen data. And we're going to use cross-validation now and essentially turn the problem from unsupervised to a supervised, where each node serves as the outcome that we want to predict. So for each configuration, we partition our data like two different folds, and each fold serves as the test set each time. So we estimate like for each fold the causal graph using this configuration. And then for each node, we fit a predictive model from the training data using only the Markov blanket variables. And then we can see the performance for this node on this fold with this configuration on the test data. And in the end, we have we average over all nodes and folds, and we find the expected predictive performance of that configuration. Okay, so in the end, we return the causal graph produced by this winning configuration when trained on all of the data. The cost of the algorithm is that it builds like for each configuration in each fold in each node a predictive model. So it's relatively high. But you know, if you have a lot of data, you don't need to do like a full cross validation. If you have too many nodes, you can subsample that. So it's not like too prohibitive, I hope. But note here a subtle point. We estimate the performance of the configuration. We estimate the performance of the algorithm of the pipeline that produces the causal graphs. We're not estimating necessarily a given causal graph, the predicted performance of a given causal graph. We estimate the performance of the pipeline. And we use then the pipeline that on average gives you the best causal graphs to build your final causal graph. This is the one, this is your final choice, let's say, to use built on all of the data. So you don't lose any data for estimation. All right, but as I said, there is a problem here. The problem is that we can also obtain optimal predictive performances with supersets of the true Markov blankets. Essentially, the complete graph is also going to achieve optimal performance. So we need to penalize for the inclusion of false positives in the true Markov blankets discovered compared to the true ones. So let's see, the true graph containing the true Markov blanket members will achieve the best performance over everything else, over all the other graphs returned by any other configuration. Now, if you have false negatives, so if you have a configuration that misses some like members of the Markov blankets, you won't have all the predictive information in your models, and you will achieve a smaller performance. So you will not select configuration alpha 3. But if you have a configuration that returns graphs with false positive members, larger Markov blankets, then conceivably we'll have the same predictive performance as the true graph. Now, since it has some false positives, you may be overfitting a little bit, and the performance in practice, you may get to see that it's a little lower. But if you have a very powerful classifier, let's say, then it could be equal. So here's our principle that we propose to solve this problem. You find a configuration that actually gives you the best performance as estimated. But then this is not what you actually return. What you actually return in your final choice is the configuration that is statistically indistinguishable in terms of performance with the winning configuration, but it has the minimal average size of the Markov blankets. So it returns the sparsest networks, the smallest Markov blankets, while still achieving a performance that is indistinguishable from the best, up to using a statistical test. So let's see now how we determine actually this statistical indistinguishability. There's another idea that we kind of contribute here. So we want to test statistically whether we define the difference of the average performance obtained by the graphs produced by configuration alpha star, the winning configuration, and some other configuration. And the null hypothesis is that this difference is 0. And if we cannot reject it, we accept it. And we accept that the two performances are actually not different. Okay, so the way we do the test is that we need to estimate performances, and we need to estimate performances on unseen data, out of sample predictions of these models. And so we pull together all of the out of sample predictions from all faults during cross-validation in, let's say, for one node at least, that is binary. I'm pulling together here the predictions from all faults. Let's say I did a 3-fold cross-validation using like the best configuration and using like some other configuration. Okay, so I have my based on this, like I can use the data that I have to see my performance. And in order to test whether on average these two like vectors lead to the same performance, I'm using a bootstrap technique, sorry, a permutation-based technique, where I produce two new vectors where I randomly select like to swap some predictions. Why am I allowed to do that? Because under the null hypothesis, the averages of these two like procedures are the same. So I'm allowed like to, under the null hypothesis, switch like and swap. So based on that, I can calculate like a p-value and perform the test in a non-parametric way. Okay, so the next problem is how we actually measure performance. Well, we can use like, if we have only continuous variables, any metric for continuous variables, like the mean squared error. And if we have discrete variables, we can use something for discrete variables like the AUC, or accuracy is not recommended. But if we have mixed type of variables, then we need to average out of the performances. So you cannot like add AUCs and mean squared errors. So our solution to that is to actually use a metric that can be defined, a metrical performance that can be defined for any type of variable. And this is the mutual information, and specifically the mutual information between the true values of the variable x and the predicted values of the variable from the model of for x built using only its Markov blanket. So in fact, this is the definition for continuous variable of the mutual information. It requires, in order to estimate it and compute it, the density here, the joint density of the predictions and the estimated and the true values. And in order to compute it and estimate it, like we assume a bivariate Gaussian distribution, in which case there's an analytical formula for the mutual information, where R is the sample Pearson correlation. And for discrete variables, the integrals turn to like summations, and the probabilities are estimated with maximum likelihood, meaning like we just like count how many times we see these two values together. So this solves the problem of averaging out over different types of variables. So our design choices for the algorithm, of course, you may try different ones using the same ideas, but the results I'm going to show you use these choices. For our predictive learning algorithm, we use random forests. It's relatively computationally efficient. You can use it for both continuous and discrete types of outcomes and mixed data. Of course, random forests are not always optimal. I would prefer an automated machine learning approach, but this would be probably too expensive computationally. For the performance metric, we use the mutual information, so we can use it for mixed type of variables, but it does make some parametric assumptions. And for the sparsity penalty, we use this hypothesis testing of statistical equivalence of performance. It's a non-parametric test, which is good, but it does have some computational overhead. So using these choices, we can apply the methodology to any type of data with variables that don't make with functional relationships that can be linear or non-linear on both like Bayesian networks and DAGs, as well as maximal ancestral graphs. And indeed, any type of causal model that induces Markov blanket. On the minus side, as I said, it is a bit computationally expensive. So this is our suggestion, and while we tested, are there any other approaches? And indeed, there are. The first family of approaches is what I call like approaches that balance the fit with the complexity. The in-sample data fitting specifically, how well the causal model fits the data with the causal model complexity. Some prominent like approaches that have been tried specifically on causal tuning causal algorithms is the BIC score and the AIC score, which can be defined for continuous or discrete, and recently for mixed types of data. So the AIC, for example, score, it balances the log likelihood of the in-sample data fitting of the model with the kappa here, K is the number of parameters of the model. Okay, so this is how we choose model. It has been used like in many other contexts and settings, of course, this methodology. The main difference from our methodology is that it uses the in-sample data fitting, not the, you don't like validate on out of sample, you don't do a cross validation. And the other main difference is that you need to be able to measure model complexity, which is only possible if you make some parametric assumptions. Okay, so these approaches are mainly applicable to Bayesian networks with one exception. There is a big score that can be calculated for MAGs only if the variables are continuous. Another approach that has been proposed in the literature is based on measuring structure instability, and we choose the configuration that leads to the least the minimal network instability. This is the STARS algorithm that was initially proposed not for causal discovery, but to tune graphical lasso. But it has been used like to tune causal discovery algorithms in this works here. It's suitable for any type of data. So like OCT runs everywhere and anywhere. And it is computationally inefficient, as we're going to see. The way it works is you subsample your original data, you produce many networks using the same algorithm from the subsamples, and then you measure the edge frequency, ignoring the direction, which gives you the edge instability. And when you average out, it gives you the network instability. So as presented, the method ignores, first of all, how well the graph fits the data, and ignores the causal orientation of the data. All right, so which one works best? And do these methodologies, if any of them, is robust enough and good enough to lead to tuning causal discovery algorithms? That is the question. So we set up a quantitative experimental comparison, where we use the OCT, the methods using BIC, IC, and CG and DG, which I remind you, these are for mixed types of data, the STARS algorithm, and we also include random guessing as a baseline, and also the best and the worst case, essentially. So what would be your best choice and your worst choice? We evaluate these algorithms, how well they select causal discovery algorithm on data sets and on causal graphs. We simulate the data. We try to reconstruct the causal graphs that generated them, and the causal graphs can be either use only continuous variables with linear or non-linear relationships, discrete variables, or mixed. The causal models can be the Bayesian networks or MUGs. And the way we evaluate them is how good how good choices they make by using the structural Hamming distance, or SHD, which counts the number of operations returned required to transform the learned graph to the true graph. So lower is better. Now, the best case that I mentioned here corresponds to the choices that we would do if we knew the true causal graph. We call this the oracle configuration. It's an oracle that knows the causal graph and selects the algorithm that gives you the results that are closest to that. So I'm going to be presenting the results according to the delta SHD, meaning the difference between the SHD achieved by an algorithm and achieved by the oracle configuration. So lower is better and 0 is optimal. The 0 means the algorithm selects the causal discovery algorithm, the tuning algorithm selects the causal discovery algorithm that returns the graph that is closest to the true one. And we simulate each point that I'm going to show is an average over 20 causal models with these settings here, unless otherwise stated. So let's see the results. Now, in terms of configurations, we try lots of different algorithms, like the PC variants. There are several PC variants, like PC stable and CPC, and the standard PC with different independence test and different significance level. So overall, in these scenarios, we have 51 configurations. When you go to mixed MUGs, there are not that many algorithms that run, so we have fewer configurations. And you can see that OCT runs on all these scenarios, STARS run on all these scenarios. The other methodologies only run on certain other scenarios. So these are the first set of results. We have here the delta SHD. As I said, 0 is the best we can achieve. We have OCT in red, BIC, IC, and STARS with green. Random guessing with gray, and the worst case, which gives you an idea of the range of your choices from 0 to the worst, is with black. And here in this first set of experiments, we will vary the type of data, whether they're like continuous or discrete, and whether they're mixed. And here we vary between like Bayesian networks, DAGs, and MUGs. Here we vary like the number of nodes. So going like to larger networks. Here we'll vary the number of samples, going to larger sample sizes. And for MUGs specifically, the number of latent variables in the causal model. So overall, like the red dot here is robustly one of the best methods and relatively low compared to the other methods. We can claim based on these results that it performs reasonably well. However, these results are on simulated data that come from, let's say, linear relationships or multinomials, and they come from randomly generated graphs. So let's make the problem a little more difficult. And specifically, let's have causal relationships that are nonlinear. So from this Joe Ramsey paper here, we produce data that are nonlinear and non-Gaussian using different like functions here. And some of these like functions really violate the assumptions of AIC and BIC. So we can see that again, like OCT is quite robust in performance towards lower values, except like this case, the logarithm, for some reason, we have to investigate. But here what happens, I mean, for me, the most important thing is that AIC and BIC in this case are really bad. Okay, so you can see, for example, AIC is actually is worse than random in this case. Okay, so next thing is like, okay, we are simulating these causal relationships and the causal structures, and the algorithm works like relatively robustly. But are these like type of data in graphs what we're about to encounter like in practice? Do they actually resemble real like data and causal models? So we try to actually test the performance on real like causal graphs. But the problem, of course, is how do you get real like causal graphs? So we use like a resimulation technique. Let me explain. We learn a causal graph using some standard algorithm like FGES on real data. And now we consider the learned graph like as our gold standard, hoping that since it's learned on real data, it has the properties of true causal graphs that we encounter in practice. The density, let's say, and the connectivity that you find in practice. And for each node F, we fit a predictive model, a non-linear, non-parametric, like a random forest. And we use this as the gold standard for the causal relationships. And then we resimulate new data using this causal model as our gold standard. Hopefully, this is going to give us like causal graphs, causal relationships, and simulated data from these models that are closer to the real thing that we expect in practice. So we see here the evaluation of the algorithms in terms of how good choices they make to select the best causal discovery algorithm. And again, like OCT is pretty like robust. There are a couple of data sets that its performance is not very good, like the wine data set. But overall, like it stands well, I think. Now, coming back to one thing that I haven't mentioned is whether we really need to penalize for sparsity. So we include in this set of experiments the version of OCT that doesn't penalize for sparsity and returns just the best performing model, best performing like causal discovery algorithm configuration. We also include in this set of like experiments a dummy algorithm that always returns like the full network, and a dummy algorithm that always returns like the empty network. And what we see here is that if we don't penalize for sparsity, OCT performs really bad in these scenarios. And then after that, like it actually, its performance is on par with OCT when penalizing for sparsity. Here, like in this histograms, we plot how many times like an algorithm chooses the full network, the dummy algorithm that always returns the full network or the empty network. We see that stars often chooses the empty network, and OCT often chooses like to return the full network. And OCT, when penalizes for sparsity, removes like to grant this effect. All right, so in conclusion, we aim to select the best, So in conclusion, like the ideas that we offer is that we evaluate the causal models with respect to their predictive power, each node predicted by its Markov blanket, and this turns the problem to a supervised problem. And so then we can employ out-of-sample performance estimation protocols to estimate performances. We use mutual information to enable averaging across different data types, and we consider both the predicted performance and the sparsity. The experimental evaluations show that it performs robust and relatively well to the other methods across a range of settings with varying sample size, types of functional relationships, and the like. Now, where do we stand? I think there's significant room for improvement in terms of quality and computational efficiency. This is by no means the end of this line of research, hopefully just the beginning. And results do vary, keep in mind, with the choice of causal metric and how you measure the quality of the causal model that you select. Are we ready for automated causal discovery? So that you just enter your data, click, and the system tries dozens of algorithms with hyperparameters and configurations to give you the best. I think this is a good first step, and we'll try to like automate it as much as possible. So thank you very much. I'll stop here, and I'm ready to take your questions.